We have seen how we can take the area under some derivative function, in this case f prime equals x cubed minus 4x squared plus 3x plus 5. So it's just some red graph here that represents a derivative. And we can find the rectangular area by taking the height, which is f prime value, and multiplying by width, and that gives us the area. And we can add up this area to find out that area underneath the curve. And one of the key ideas from the previous day was that we could make this approximation better and better and better by making the delta x smaller and smaller. Or essentially, we can use a limit and let delta x go to 0. And the narrower those rectangles are, the better it's going to fit the area underneath that curve. So a couple different ways we can express this, and we want to get used to just seeing this in a few different ways, is that the delta x is the interval width or the distance from A to B. So we notice that we express that distance as B minus A. That's our interval width from here to here. So we're going to divide that by the number of intervals, which we call n. And we're going to, if we want better approximations, we're going to let the n go to infinity. The number of intervals gets more and more and more, which makes our delta x narrower and narrower, and that'll give us a better approximation. So our summation form looks like this. It's the height, f prime, times the width, and this summation just means we're going to add up all those rectangles from A to B. And we're going to see this in a few different ways. So that's one way to see it, the one way that we're going to have it seen in some problems. We could also make a limit. So when we talk about the making it better, we're going to make the limit as n goes to 0. So it's the same expression. These are exactly the same expression, but one is using a limit. And we can think of this as similar to when we started with the definition of the derivative, the secant line sloped or slope between 2 points, and then we let the distance between those 2 points go to 0 to get a tangent slope. And this is similar. We're taking kind of this rectangular blocky area and we're taking a limit, and that will make the area much smoother, and it gives us the exact area when we take a limit. It's going to look like this. Again, the only difference between these two expressions is that we are using the limit and we've now switched out the delta x with an equivalent expression b minus a. So remember that b minus a over n represents delta x, and this just allows us to take a limit for n going to infinity. So this is just finding areas of rectangles and adding them up. We're going to see all sorts of different problems. So we just want to get used to, you're not going to need to do anything right now, but we just want to get used to seeing this in different ways and trying to recognize that they are the same thing. So in its simplest form, again, it's just height times width, and the sigma means we add it up. We've kind of introduced this limit so that we can use narrow rectangles. Now we're just going to see what it looks like when we express this. And again, we're going to introduce a little bit more expression here. So this f prime graph is x plus 1, so it's a linear equation with y-intercept of 1. And we want to estimate this area. Well, this area is going to be the f prime times delta x. So notice that here the area is red. In red is my height. The green delta x is my width, and I'm going to do it from 0 to 4. And that's going to give me all the areas of those rectangular blocks underneath that curve. Now, again, if we want to let this be more of an accurate area, we need to let our delta x go to 0. So we put it into limit form, and the limit as n goes to infinity. This part represents our delta x going to infinity, so the interval width, which is 4, divided by n, which goes to infinity, and then we have the height of the function in red here, but we just need an expression that's going to replace the x. So that expression that we're going to use to replace x is going to be this one here. Okay, we're going to use x equals 4k over n. So why is it 4k over n? Okay, I'm just going to write it in because that's what we're going to use, but then we have to figure out why is it 4k over n. Okay, so the 4 is going to help us establish a starting point here. So we have here, so I should say the 4 is going to help us establish the ending point. And if we notice that we're starting at x equals 0, well, that means then that if x equals 0, we need to get 0 when the k is equal to 1. So notice there's our k value. Okay, I'm just going to use a highlighter here. There's my k equals 1, and there's where k is equal to 1. And that's my starting point, and I need to have an x value of 0. So that 4k over n must be equal to 0. And I get that because 1 divided by infinity is going to be 0. And that 4 just becomes insignificant, becomes 0. So that's how I get the starting bound. Okay, I'm just going to do that in yellow. And then I need to get to the ending bound with that same expression. Okay, so the end is at 4, and I get that by plugging in infinity, because n, remember that n goes to infinity at the end, and so I get infinity divided by the infinity, which is our n in our expression, so that n infinity is from the end point here. The bottom infinity is as n goes to infinity there, and when I do 4 times infinity over infinity, that equals 1, and that gives me my end bound, which is going to be equal to 4. So this then represents the end coordinate. So this is the correct expression. This expression over here then must represent the correct expression that expresses values of x. So then I'm just going to put that into my expression, and this is what my summation looks like when I put it into the the sigma form of this. Now this is a complicated way of writing it, but if we work backwards, we can see that it just goes back to this height times width. So we have our, again, just to kind of summarize this, we have our width here, that's our delta x. We have our height here, that's our f prime. This part represents the delta x. That's our f prime or y. What's this 4k over n represents are x values that we can use based on our n and k to generate values from 0 to 4. So the end expression looks like this. If I want to find the area under that curve, I'm going to have x plus 1 times delta x, or when I put it into k and n form, 4k over n plus 1 times the width 4 over n. And if we let n go to infinity, we can then get exact area. We could also use the same expression by choosing different n values. We could maybe have 4 intervals. We let n equal to 4, and then we would use that. And then we could use n equals 20 rectangles, and then we just substitute 20, replace that with 20 in our expression. We'll look at one more example of how we can go from the height times width into this more complex sigma expression. So here I have the square root of 2x plus 1 in red, and I want to find the area underneath that curve from 0 to 3. X is 0 to x is 3, so I kind of shaded that in with those rectangles. And to do that, I'm going to take the height of my graph, which is square root 2x plus 1, I'm going to multiply it by whatever that width is. If we want to make this a perfect area, smooth area, we use a limit and we apply a limit to this. If we're going to apply a limit of n going to infinity, we need to express it with n's and k's. So then I need to be able to find, first of all, and I'm going to color code this. First of all, I need to match the delta x. So there it is over here. This represents my delta x. And it's going to be the interval width of 3 divided by n. And now at this point, I can use as many n's as I want. And in fact, I can make an exact area by letting n go to infinity. The other part of this expression is this x part here. We need to replace x here with that expression 3k over n. So how did we get 3k over n? Okay, well, we're going to start with k equals 1. Okay, n goes to infinity, so that's going to give me 3 times 1 over infinity. That's 0. That gives me my starting bound of 0 here. Okay, when I plug in n is infinity. And why is it 3? Because I need to go from 0 to 3. So when I do my infinity divided by infinity, I need that 3 to indicate my interval width. So this 3 in my x expression represents the interval width, and then we're going to do k over n. So to go from 0 to 3 in this case, or the 0 to the interval width of 3.